Let me do an example of a linear differential equation that is homogeneous, not constant coefficient though. Dy dt equals 4 cosine 2t y. So we're in this box, right? We just have some stuff with t times y, and we know that the general solution looks like this. So the answer is y equals c times e to the, and then we have to do the antiderivative of 4 cosine 2t dt. Okay, well, we can do that. The antiderivative of 4 cosine 2t is going to be 2 sine 2t. And there we go. That's the general solution. Now I also have an initial condition of y of 0 equals 1. So we plug that in. It's got to equal 1 when we plug in a 0. Now sine of 0 is 0. E to that 0 is 1. So actually c is just 1. So final answer, e to the 2 sine 2t, done. Okay. Now, if we return to our table and we look at the left column, where we're not homogeneous, where we have the plus b of t, plus b of t. Well, we're in a little bit of trouble here at first because we are not separable. Right? The plus b of t is messing that up. You don't have t stuff times y stuff in that way so that you can separate them. So not separable. Unless, yeah, well, no, just not separable, I guess, unless the b of t were a constant. If the b of t were a constant, then it would be autonomous, so it would be separable, and you'd be okay. But let's assume the b has t in it, then it won't be separable. Okay, so there's going to be more to do to solve this analytically. Let me just take this moment to remind you that you can always do a slope field. You can always do Euler's method to get a numerical table. That's always an option here. Can't do a phase line because of the t, right? These are phase lines only apply to autonomous differential equations, and these are not autonomous. But you can do a slope field. But to attack this, in terms of an analytic solution anyway, getting a formula, I want to add a second linearity principle. So we talked about the first linearity principle that applied to homogeneous ones. The second one is going to apply to non-homogeneous ones, but you'll see in a second that it involves homogeneous differential equations as well. And it's a little bit harder to describe, and so I'm going to do it on its own page. So if you have a linear differential equation, and it doesn't have to be constant coefficient, let's say you found one solution. I'm going to call it yp. It's one particular solution. That's what the p stands for, particular. So somehow, some way, you came up with one solution, just to the differential equation, without an initial condition taken into account. So let me be clear. No specific initial condition satisfied. So you found one that solves this, but maybe it doesn't match your initial condition, or you just want the general solution anyway. Well, here's the thing. The general solution will be y equals, and what you do is you take the one solution that you found, okay, and then you add the general solution to the corresponding homogeneous differential equation. And when I say corresponding, what I mean is it's got the same a of t as the one you're working on, but you just drop the b of t. Just drop the b of t, okay? So this is really nice. It means it says that finding one particular solution is enough to then get you the whole thing, because what you do is you just add on the general solution to the homogeneous differential equation, and that guy will have your C in it, right? It'll be C times something, as we mentioned in the first linear principle. And that C will give you the freedom to now solve any initial condition. But the point is that these will all satisfy the differential equation, so you've already got that done. Of course, that still leaves the not small problem of how do you get that first particular solution. And so that's where all the emphasis will be once we get this under our belts. It'll be in finding that one particular solution. So again, getting the homogeneous one, we saw that that's not too bad because that's always separable. It involves doing an antiderivative that hopefully you can do, but let's assume we can do that. That's fine. And then if we can get the one particular solution, then this combination will give us the whole thing. So it's all about then finding that one particular solution. Okay, I want to show you an example of this playing out. I want to show you an example of the linearity principle playing out. So here we go. Let's say we did dy dt equals negative 2y plus e to the t. Okay, so our a of t is negative 2. It's actually a constant. So this is actually a constant coefficient linear differential equation. And then plus e to the t, that's our b of t, non-homogeneous, right? Okay, so now, to show you the extended linearity principle, though, I have to kind of cheat, and I have to give us one particular solution. Remember, that's the whole thing. That's what we now, after understanding this, we're going to go forward and talk about finding the one particular solution. But for now, just so I can show you the principle, let me give you one particular solution. So please understand that I'm not going to show you where this came from, but let me just give it to you anyway. E to the t over 3. And I'm sorry, the over 3 wasn't supposed to be in the exponent. Sorry, it's supposed to be down on the outside. So 1/30 to the t. Sorry about that. By the way, here, let's do a quick check that it is a solution. And again, you don't know where this came from. Let's assume that there's some method that gives us that. Okay, so let's check it. So on the left-hand side is the derivative. So the derivative of 1/30 to the t, well, is 1/30 to the t. And then now on the right is negative 2 times y. So that'll be negative 2/3 e to the t plus e to the t. And yep, that equals 1/30 to the t. So it checks out. All right. So 1/30 to the t is one solution. It satisfies some initial condition. I guess it satisfies y of 0 will be 1/3. That's the initial condition. Now, if that was the initial condition of our problem, we'd be set. In fact, let me give us an initial condition. Let's say y of 0 equals 1. Okay, so we found a solution that satisfies the differential equation but does not satisfy this initial condition. It satisfies another initial condition. So we're not done. Okay. But now, and here's the point of this example and what I want to show you. The extended linearity principle says, okay, well, all you have to do is take that and then add the general solution to the homogeneous differential equation. Now, we have to figure that out. So the homogeneous version of this differential equation is dy dt equals negative 2y, period. You just drop the b of t. This is the associated homogeneous differential equation. Okay. Now this one is constant coefficient, so this was like the bottom right in our table. We don't even have to think about this one. The solution is, and I'll label it yh for homogeneous, it's just c e to the minus 2t. Done. So that one was that one is as easy as it gets. We know this one, don't have to do any work. Okay, so therefore, putting it all together, my general solution would be y equals, and I take my particular solution, right, that was a solution but didn't have the right initial conditions, and then I'm going to add the homogeneous general solution. And I claim that that's the general solution for this differential equation. And now I have a c that can be used to get any initial condition. So if I want y of 0 equal to 1, put a 1 in for the y, put a 0 in for the t, that'd be 1/3 plus c. Both exponentials become 1s. So it looks like c should be 2/3. So my solution to my initial value problem would be y equals 1/3 e to the t plus 2/3 e to the negative 2t. Let's just check that. Because, yeah, I mean, we checked the 1/3 e to the t, but we've added a whole new term, so we better make sure that everything still checks out. So the derivative, dy dt, okay, so that'll be, well, the derivative of 1/3 e to the t is 1/3 e to the t. And then the derivative of the second piece, either the minus 2t will still be there, and then a negative 2 will pop out. So we'll have minus 4/3 e to the minus 2t. So that's derivative. That's the left hand. That is the left-hand side of my differential equation. Now on the right-hand side, it's supposed to be minus 2y plus e to the t. So minus 2 times my y, which I plug in the formula, plus e to the t. And we want to see if the left and the right equal each other. So I see that I have, right here, I have negative 2/3 e to the t. And then I see plus 1 e to the t. So that will give me a 1/3 e to the t. And then I see I have minus 4/3 e to the minus 2t. So yes, it works. It matches. That's a check. So this is the answer.